Okay, so we are now live. Close this and share the screen. Okay, so again, a reminder to send questions for the final QA of tomorrow if you have questions regarding the course or doubts that you have. Uh, Also arising from these last lessons that we have been doing that are sort of treating some more advanced topics in reinforcement learning by means of this paper reading modality that I'm trying out. Um, Also, a reminder that you should answer the qualitative assessment for the overall machine learning course. And yeah, so I also have a code that I will share with you on Classroom for this part. Um, okay, so today we're going to talk about uh, another algorithm that we are going to have among the possible choices for the among the possible assignments actually for the projects. And this algorithm is called GALE, Generative Adversarial Limitation Learning. So uh, what's the setting here? So the goal of imitation learning overall is that of having an expert providing sample trajectories. So there is an expert who has a policy that is unknown to us. By using this policy, the agent interacts with the environment, and the only thing that we can observe are the trajectory that are generated by this expert. By trajectory, I mean, as usual, the state and actions that are visited by the expert. So by looking at this, we want to recover a new policy that should be imitating the expert uh, as, uh, as much as possible. So there are different ways of doing this. One is, for example, doing uh, the so-called behavior cloning, where we treat this problem as a supervised learning problem, where basically we have a data set of um, samples and labels, where the states represent the samples and the actions are the labels. And this data set is used to train a classifier or whatever you want to use for that uh, in a supervised way. Another approach is the so-called apprenticeship learning, where you basically do first inverse reinforcement learning and then reinforcement learning. So what is inverse reinforcement learning? By looking at these trajectories, the goal is that of recovering the reward or cost function. As you know, I mean, the reward function and the cost function are the same thing, just the reward uh, is in a positive sense, the cost function is in a negative sense, right? So the goal is that of recovering the reward function that was leading the expert to that behavior, and then by means of this reward function performing reinforcement learning on top of this. Um, and why would you want to do that? Because it's well known in literature that the reward function is the most succinct representation of a task. This is another approach. There are pros and cons in all of these two approaches, and in this paper, basically what they're trying to do is trying to reduce as much as possible the cons of doing the latest approach that we discussed, so inverse reinforcement learning plus reinforcement learning. And they do this by means of GANs. I think you have seen this already in the machine learning course, generative adversarial networks. And we're now going more in the details by looking at the paper. So I will not spend more words on this, but they basically are able in this way to achieve better results than standard inverse reinforcement learning algorithms that you can find in literature. Okay, so let's move on then. So as usual, we start from the abstract, and so consider learning a policy from example expert behaviors, which is what we just described, without interaction with the expert or access to reinforcement learning signal. So why without interaction with the expert? Because, as I said, the only thing that you observe are the trajectories that the expert generates. There is no possibility for the uh, agent, for the learning agent in this setup, to query the expert to say, hey, what would you do in this state? So there is not this possibility. And also, you don't have access to a reinforcement signal. Why? Because that's exactly what you're trying to recover, sort of, because you want to understand what is the reward that is the reward function that is being used by the expert. So you don't know that. You don't have access to this. You only have access to the environment without the reward function. So they propose a new general framework for directly extracting a policy from data as if it were obtained by reinforcement learning following inverse reinforcement learning. So we are interested in a specific setting of imitation learning, the problem of learning to perform a task from expert demonstrations, in which the learner is given only samples of trajectories from the expert. So it's not allowed to query the expert for more data while training, and it's not provided reinforcement signal of any kind. So this is what we just described. There are two main approaches suitable for this setting, which are the ones that I presented before: behavior cloning, which learns the policies to supervise learning problem or state action pairs from expert trajectories, and inverse reinforcement learning, which finds a cost function under which the expert is uniquely optimal. Or in other words, finds the cost or reward function which better explains the behavior of the expert. Hmm? So behavior cloning is simple, while appealingly simple only tends to succeed with large amount of data. Why? Because it's casted a supervised learning problem, and as usual, you need a big amount of data, and there's also another problem um, that typically when you do behavior cloning, you tend to have a compounding of error. So let me go a second in uh, whiteboard mode. Actually, you will have, if you go on my um, YouTube channel, there is a lesson, seminar in the seminars course. There is a seminar from last semester, so the spring semester, where a professor from Cornell University, previously at Microsoft Research, was explaining his research, which is exactly on this topic. It's very interesting. If you have time, look at that. So it was explaining exactly how to improve imitation learning when you have this kind of problem. But anyway, let me try to explain a second uh, the problem. So let's say that we have uh, a bunch of trajectories from the expert. Hmm? Oops. Okay, so this is one trajectory. Then we have something like this. And for simplicity, let's assume that we have only three trajectories. Hmm? Okay, so this is our expert data. This composes our data set. So this is the initial uh, state, and this seems to be from the collected trajectories that it's the goal state. Of course, again, we don't have this information in an explicit way. Now, what happens? Suppose we do um, behavior cloning, and our classifier um, learns um, a certain policy that ends up during the execution of the trajectory to behave in this way. Now, you see there is already a problem here. So it's not that there is a big error in these arrows compared to the ones that are uh, over in the dataset. However, as you notice, their inclination is slightly incorrect. So I have also exaggerated this to make it more clear, but there is a small error here, a small error here, a small error here, and this is compounding and moving the trajectory of the learner to uh, a distribution of states that has not been seen in the dataset. So if you have this set up, then you might end up, again, here I'm exaggerating, but you might end up in a state over here, and here you don't have any samples from the expert. So you don't know what's the behavior that you should follow. And this leads to higher and higher errors, where you might even end up here. So your error might be as big as this, and it compounds in a compounds, sorry, in the number with the number of time steps in a squared way. So typically the error is squared uh, in the number of time steps that you need to follow the imitator's policy. So, and I hope again this explanation is clear. The issue is that while moving with small errors, the imitator, the cloner, the learner might end up in a space where you are in states where the expert didn't provide any samples. So basically, the issue is that the um, state distribution of the learner does not coincide with the state distribution of the expert, and this leads to this issue that they are describing in the paper. Let me again share now the paper. Okay, so inverse reinforcement learning, on the other hand, learns a cost function that prioritizes entire trajectories over others. Unfortunately, many inverse reinforcement learning algorithms are extremely expensive to run. Why? Because, as I mentioned, you need to do first inverse reinforcement learning, and then you have to do reinforcement learning in an inner loop, meaning that you need to do this for every iteration of inverse reinforcement learning. Every time you try to do an optimization in of the cost function, then you need to run reinforcement learning. So it's very expensive. So we design instead an algorithm that tells us explicitly how to act by directly learning a policy. And to develop such an algorithm, they introduce this GALE, which is a new model-free imitation learning algorithm. Then they show that the resulting algorithm is connected to generative adversarial networks, and which is a technique from deep learning that has led recently to success in modeling distribution of natural images. And this algorithm uh, uses generative adversarial training to fit distribution of states and actions that define the expert behavior. So questions so far? Uh, questions so far? Again, I just answered this question. Uh, Again, as I mentioned, the results of the homework will be published in 2 or 3 days. I've been correcting them the whole week. There are many students. Uh, I mean, it takes the time that it takes. Okay, so as usual in the papers, we have this background section where they provide information for the reader regarding what's the setting that we are in. So as usual, the formalization is that of having state and action spaces as NA. And here they characterize capital Pi as the set of all stationary stochastic policies that take action in a given states in S. Then there are successor states that are drawn from the dynamics models. This is the transition function. And we work in the gamma discounted infinite horizon setting. So they use gamma because of that. And they will use an expectation with respect to a policy pi belonging to this set of stochastic stationary policies that take action in A and S to denote an expectation with respect to the trajectory that it generates. So this is the definition, the expectation over the cost over the trajectory generated by the policy is defined as the expectation over basically the trajectory, the cost of the trajectory for a state and action visited in the trajectory, discounted by gamma, starting from a certain initial state that is sampled from the possible initial states, and the action is sampled from the policy as usual, while the successor state is sampled from the transition function, which is again unknown to us because we only have access to the environment without knowing its transition probabilities. So they denote the expert policy. This is typical as pi of A, where E denotes expert. So inverse reinforcement learning, they also give some background on inverse reinforcement learning, which is, suppose we're given an expert policy pi E that we wish to rationalize with inverse reinforcement learning. For the remainder of this paper, we will adopt maximum causal entropy inverse reinforcement learning, which fits a cost function from a family of functions C with this optimization problem, which we're now trying to understand. So again, so this is pi E is provided, we don't know the policy exactly, we only know the trajectories that are generated by this policy, okay? So we can only compute the expected cost of this by looking at these trajectories. So this expected cost is an expectation over, it's an empirical expectation with respect to the trajectories that are generated by the expert. So we're now looking for a cost function that explains this expert behavior at the best, which is basically then assigning the smallest cost, the lowest cost to the expert policy, and a higher cost to any other policy. So any other policy will have maximum, they're trying to maximize the difference between the cost of any other policy and the cost of the expert, which should be the minimum one. This other policy, however, will be a maximum entropy policy. And here, given this is a minimization problem, they have the minus in front of it of the entropy in order to maximize the entropy. So a maximum entropy policy was cost will be anyway higher than the cost of the expert policy, And so they're trying to maximize this difference between this cost. So the optimization here is over the cost function. So there are two optimizations here, as you see. One is over the policy, the other one is over the cost function. So maximum causal entropy in reinforcement learning looks for a cost function C in C that assigns low cost to the expert policy and high cost to the other policies, thereby allowing the expert policy to be found by means of a certain reinforcement learning procedure, which is exactly what I was saying. It's trying to minimize this term over here. So minimizing the cost and maximizing the entropy. And again, why do you want to use a high entropy policy? Because you don't want to commit to any specific choice when you can have valid alternatives that can be used as well. Okay, questions? What is the set of all stationary stochastic policies? Okay, so here they introduce this pi that is basically just characterizing what is the policy, the kind of policy that we're using. So it's a set of policy that can take actions in A and S. So this is restricting the space of policies to policies that belong to that can act in this action space and that can operate in this state space. All these policies will have to be stationary and stochastic. I mean, stochastic. I mean, we know the definition of stationary and stochastic, but we are using. We choose to work with this kind of policies in this setting. So, for example, it could have been decided that we were operating with deterministic policies. This is not the case. So we are limiting um, restricting ourselves to the setting of stochastic policies. So again, this is just the characterizations of the policies that we're considering. So stationary, stochastic policies, and of course they have to operate in these state and action spaces S and A in order to be valid for our analysis. Okay, can you repeat the formula? Sure. So okay, so here where we here there is nothing new, right? So this is uh, sort of standard solution that we're trying to find, which is we have a cost function or a reward function. So if we have a cost function, we try to minimize the cost function, right? Or if this was the reward function, we would have had a maximum over here. But so we have a cost function. So we try to minimize the cost function in expectation with respect to the empirical expectation that we can get computed by means of the trajectories that our policy generates. And we have also this additional term, which is an entropy term. Again, we are minimizing the negative of the entropy, which means that we are maximizing the entropy, right? So we are seeking here for a policy which minimizes the cost function and is also a maximum entropy policy. And so this is what is happening inside here. And in here instead, we're trying to maximize the cost function in such a way that we can find a cost function that assigns a low cost to this expert behavior and a higher cost compared to the one of the expert to any other policy that we might find here. Why? Because we want to find a cost function that explains at the best the behavior of the expert. So the cost function should be minimal for the expert and higher for any other policy. So as you see, these two objectives are contrasting each other in a sense, because here we're trying to get to the minimum of the cost function, of the cumulative cost function. This is trying to find the best policy that it can be found given this cost function. But this is trying to maximize this difference that says, okay, now let me find a policy, sorry, a cost function for which uh, this is very well explained, but this is put in a difficult situation. So this other policy is in a difficult situation. So there you can already see a bit how this is going in the direction of adversarial training, right? Because on the one hand, we have something that is trying to do its best to minimize this cost function, and on the other end, we have some other thing that is trying to uh, find a cost function for which every policy that you can find will be in a difficult situation, because the this cost function has to best explain the policy of the expert. Okay, I hope this is hope this is an answer that is valid. If not, please uh, ask further questions. I'm more open that spending more time into this. So, is this the case of an agent that follows the motion of a human? So, uh, it can be the case of that, or it can be the case of, I don't know, let's say you are, I mean, this is something that has been used in a paper, for example. Let's say you're playing uh, Mario Kart. So, you are the expert. I'm the person who is implementing an imitation learning algorithm. So I record the actions that you take by means of your joystick in Mario Kart, and I collect the states and actions. And then I use, for example, this algorithm or any imitation learning algorithm to imitate you uh, the best I can. This is one example. There can be many other situations where you have um, another kind of expert that can be any other expert that you cannot have other access to. So one relevant question to this might be, why would you want to do this sort of thing? Why would you want to do imitation learning over some expert instead of performing directly reinforcement learning with a hand specified reward function? The problem is that uh, typically it's very hard to specify a reward function. As I mentioned at the beginning of the reinforcement learning course, specifying a valid reward function can be extremely complex. And for example, let's say that you want to do reinforcement learning on autonomous cars. So you want to do something in such a way that you can uh, retrieve a valid, good, acceptable uh, style of guiding, of driving. Sorry, and if you have access to some experts, then you can do inverse reinforcement learning, and you can try to retrieve a reward function, and then use reinforcement learning on top of that. Otherwise, I bet none of us would be uh, successful in specifying a reward function for that. Also, because there are complex observations, so the observations might be images, for example, or sensors like lidars and stuff like that, and it's hard to manually specify a reward function that maps these states to acceptable rewards. So the idea here is I cannot specify a reward function, but what I can do is I can observe some experts and I can retrieve reward function, and then I can do uh, reinforcement learning on top of that. So is this like the concept of transfer learning where our agent try to learn from the experience of another? So it's not exactly transfer learning. So the transfer learning in the reinforcement learning setting would be I learn to drive uh, in a city, and then I transfer to a completely different environment, which is the countryside. So that this is the how transfer learning would map to our setting. It's correct when you say our agent is trying to learn from the experience of another, but it's not exactly transfer learning. Although, I mean, it's not transfer learning because you don't have a model that you can look at inside. So transfer learning has its own peculiarities. It's not exactly the same thing. So again, uh, here transfer learning would be better suited as a word in the case where you have an agent that is learning in some environment, and then you are changing the environment, and then you want your policy to transfer to a new environment which is similar but not quite exactly the same, like the driving in the city and the countryside example. Or I don't know, another example related to that might be transfer learning can be applied in the case of reinforcement learning when you want to when you learn a policy in simulation, and then you have to adapt that to the real world. So there the sensory information changes quite a bit, and that's when you apply some transfer learning. So yeah, if you have some other doubts regarding this, ask, because I think these questions that you're asking are very interesting. So uh, keep on if you have more doubts or questions, because this is good. Okay. Okay. Um, so how did they arrive to this idea of using GANs um, for the purpose of doing imitation learning? So as I mentioned, they uh, this is already can be an intuition can be already obtained from this formula over here. But to analyze that, they went into the details of what would be the learned optimal policy if we perform inverse reinforcement learning and then reinforcement learning on some trajectories performed by an expert. So um, this section is quite complex. There are a lot of propositions and proofs that we're not going through. You're very welcome to do that at home if you're interested into that. It's quite complex from a mathematical perspective, but it should be understandable. And if you want to spend time on that, you can do it, and I will assist you anyway. So if you have doubts regarding that, you can always ask for some office hours, and we can spend some time clarifying your doubts. But here I'm just going over what I think is the most relevant part of this section. Um, how do they characterize the induced optimal policy? So we will study policies found by reinforcement learning on costs learned by inverse reinforcement learning on the largest possible set of cost functions. See in equation 1, which are all the cost functions that are valid in S and A. So you can use any kind of cost function classes like Gaussian processes, neural network, and so on, so forth. Here they're investigating what the best inverse reinforcement learning algorithm can do with respect to, in terms of expressiveness, um, by examining the capabilities of this cost function. Um, so of course, with this large um, space for the cost function, inverse reinforcement learning can easily overfit when provided a finite data set. Therefore, we will incorporate a closed proper convex cost function regularizer into our study. So this is something that you typically do in general. You should have seen this in the machine learning course. In order to avoid overfitting, you'd add a cost function regularizer, which typically is convex in order to drive the learning. So this is not anything weird, and it's not, as they mentioned, particularly restrictive for the learning of the cost function in this case. It just avoids overfitting, given that you have this situation of a finite data set, and instead allows for better generalization. Okay, so in this case, the inverse reinforcement learning uh, problem becomes this one, where basically we have the same formula as before, except that we have also this additional regularizer term. Now, let's say that C tilde is the function, is the cost function that the inverse reinforcement learning finds in from the policies that are generated by the expert. We're now interested in a policy given by reinforcement learning over this cost function. And this is, so this would be the policy that is given by running reinforcement learning on the output of inverse reinforcement learning. Now, to do this kind of analysis over this learned policy by reinforcement learning, uh, they look at something that is called the occupancy measure, which is similar to the what we have seen also for the when we were looking at policy graded methods. So this is sort of telling us the distribution of state action pairs that are visited by the expert. So it's the state action distribution of the expert or of the policy. So define its occupancy measure rho pi, defined in S and A as the following, which is the uh, policy, so the probability of a certain action given a state, that multiplies um, this other term. Then the occupancy measure can be interpreted as the distribution of state action pairs that an agent encounters when navigating the environment with policy pi. And it allows us to write that the expectation is the following. The expectation for the cost function is the following, which is basically this rho that multiplies the cost function. Why? Because you can weight any cost by the probability of visiting that. And this occupancy measure is basically giving us this information determined in an empirical way. So this looks as as an expectation over the this weight that is something that depends on the policy. That's why you can then reduce everything as an expectation over the policy on the cost function. Okay. Then here there are a bunch of propositions that we're not looking at, except this one, which is saying that we can characterize reinforcement learning over this cost function that is found by the inverse reinforcement learning algorithm as the argmin over the policies of this thing here. This is basically telling us that we are finding a policy, which is a policy pi here, which is trying, so we're trying to minimize this, which means that we're trying to get as close as possible to this rho pi e, which means that we are trying to match the occupancy measure as much as possible. And this is the regularization term that they were discussing. So, which is making the uh, cost function convex. So we're finding a maximum entropy policy which matches as much as possible the occupancy measure of the expert policy. Okay, so again, here there are all the proofs in the appendix and whatever. So let's read what they say here. Proposition 3.2 is telling us that the psi-regularized inverse reinforcement learning implicitly seeks a policy whose occupancy measure is close to the experts as measured by the convex function psi star. And this suggests that the various settings of psi lead to various imitation learning algorithms that directly solve the optimization problem. Okay, so of course this depends on how you compute this psi. Okay, how this is a function again. So you are sort of just translating the problem in a different space where this is convex, and then you're doing the optimization. And then they say, okay, now what kind of psi are we looking at? So they say if psi is a constant function, then you will match exactly, you are able to exactly match the occupancy measures. In other words, if there were no cost regularization at all, then the recorded policy will exactly match the expert occupancy measure. On the other hand, if it is not constant, you will see that this is not the case. So here, this is what they are telling us in all these other sets, propositions, and in the remaining part of this section. Also here they're talking about the how this is related to dual and primal problem of reinforcement learning. So when we didn't talk about this in the reinforcement learning course, but there is a lot of theory that we didn't look at actually, where we are where basically there is an explanation on the, for example, value iteration, policy iteration algorithms as a primal and dual problem, like you are familiar with those from the operational research course. Okay, anyway, let's move on. Let's see if there are questions. No? Okay, so we saw that if psi is constant, then the resulting primal problem simply matches occupancy measures with expert at all states and actions. So this is, on the one hand, good, but such an algorithm is not useful. Why? Because the expert trajectory distribution would be provided only as a finite state of samples. So in large environments, most of the experts' occupancy measure values will be exactly 0. And exact occupancy measure matching will force the learned policy to never visit the unseen state action pairs, simply due to lack of data. So the fact that we don't have a lot of data leads us to a situation where you don't see the expert visiting other state action pairs, as I was explaining also at the beginning when I talked about behavior cloning. And in that setting, you have an issue because you don't have because you don't have the possibility of matching exactly this occupancy measure. If you do that instead, you are restricting your uh, um, policy too much, and you don't want to do that because then you're limiting a lot what you can do. And if you have also large environments, then this is leading to very bad situations because uh, you don't have data on a big amount of state action pairs, which is problematic. So let's continue reading. Furthermore, with large environments, we would like to use functional approximation to learn a parameterized policy pi theta. The resulting optimization problem of finding an appropriate theta would have as many constraints as points in SNA, leading to an intractably large problem and defeating the very purpose of functional approximation, because you wouldn't have any generalization if you have constraints for every point. So keeping in mind that we wish to eventually develop an imitation learning algorithm suitable for large environments, we would like to relax the equation 7, which is the one that we have been looking at before. Uh, we didn't look at this actually, but it's this one. So where they were basically solving this situation. Um, okay, so they want to relax that optimization problem in the following form. So minimizing this over by modifying the regularizer so that this regularizer so that this function over here corresponds to this and smoothly penalizes violations in difference between the occupancy measures. Okay, so this is not as hard as it would be in any other uh, optimization constraint that they had before. Um, so it turns out that with certain settings of psi, this equation takes on the form of regularized variants of existing apprenticeship learning algorithms, which indeed do scale to large environments with parameterized policies. For a class of cost functions, uh, subclass actually of cost functions in this space, an apprenticeship learning algorithm finds a policy that performs better than an expert across C by optimizing this objective, right, which is the objective of again maximizing the the difference between the expected cost of the expert and any other policy, and then minimizing the cost over the policy. So classic apprenticeship learning algorithms restrict C to convex sets. So there is a harder constraint of the on the kind of cost function that they consider. Um, so here now they show that equation 9, which is this one, is a special case of equation 8, which is uh, this one, with a certain setting of psi. So with this indicator function, which is defined as follows, defined by being 0 if C belongs to the class of uh, cost functions that you are considering, and plus infinity otherwise. We can write the apprenticeship learning objective as uh, this one, which is basically corresponding to this. Okay. Um, Therefore, we see that entropy regularized apprenticeship learning um, is equivalent to performing reinforcement learning following inverse reinforcement learning with cost regularizer using this uh, um, mm, indicator function, which forces the implicit inverse reinforcement learning procedure to recover a cost function lying in C. Now, what are the cons and pros of doing apprenticeship learning? So, with the aforementioned insight based on proposition 3.2, the apprenticeship learning is equivalent to reinforcement learning following inverse reinforcement learning, and we can understand exactly why apprenticeship learning may fail to imitate, because it forces pi e to be encoded as an element of C, and if C does not include a cost function that explains the expert behavior well, then attempting to recover a policy from such an encoding will not succeed. So uh, as you see in this optimization, by using this indicator function, they are forcing the cost function to belong to the category of cost functions that they like, that is convex, and it can be of different kinds, as they explain over here. But it might be that um, uh, the expert cost function does not belong to that to that cost function space. So it's restrictive. And while restrictive cost classes C may not lead to exact imitation, um, apprenticeship learning with such C can scale to large state and action spaces with policy function approximation. So they're comparing this with the occupancy measure matching, the exact occupancy measure matching. And they say, okay, on the one hand, this matches exactly the occupancy measure of the expert, and it doesn't have particular constraints on the cost function that we consider. But on the other hand, it has a lot of constraints on the usage of data, which restricts us to a setting where we cannot really apply these to large action state spaces. On the other hand, if we use apprenticeship learning, we have this other situation where we can generalize and scale to large state and action spaces, but we have a problem in the set of um, cost functions that we consider. Okay, so um, and this is what they repeat here. Constant regularizer lead to an imitation learning algorithm that exactly matches occupancy measures, but is intractable in large environments. And the indicator regularizers for the linear cost function classes, on the other hand, lead to algorithms incapable of exactly matching occupancy measures without carefully tuning, but are tractable in large environments. This is what a summary of what they were discussing so far. Okay, there is a complex analysis over this where they're saying, okay, we have this situation, so what is that we get if we perform reinforcement learning after inverse reinforcement learning, and what are the kind of results that we can get? So we propose the following new cost regularizer that combines the best of both worlds, as we will show in the coming seconds. So again, they did this kind of analysis under um, a single mathematical framework where they try to bring everything together by means of this cost regularizer function. And now they say, okay, if we can frame all these algorithms under the same mathematical framework, is there something that we can do by just replacing psi? And the answer is yes. So they replace uh, psi as follows. So if C is negative, then they use this G function. We're going to look at that. Otherwise, an infinite regularization. And G is nothing else than these other function where it's minus x minus logarithm of 1 minus e elevated to x if x is negative, otherwise it's infinite. So what is the meaning of this? The regularizer places low penalty on cost function C that assign an amount of negative cost to expert state action pairs. If C, however, assigns large cost close to 0, which is the upper bound for cost feasible for this uh, regularizer to the expert, then this will heavily penalize C. Hmm? An interesting property of this function is that it's an average over expert data and therefore can adjust to arbitrary expert data sets. Why it's an average over expert data? Because it's an expectation over this, right? Uh, so as you notice, there is something very interesting over here, which is the fact that before you didn't have any regularizer that was adapting on the data of the expert. Now it's the first time that we're seeing this. So here either we had the fixed cost function, sorry, a fixed regularizer, or a regularizer that didn't depend on the data but on the cost function. So this is the regularizer that they used in the apprenticeship learning setting. So here instead, we are using a regularizer that depends on the data. So the indicator regularizer used by linear apprenticeship learning algorithms described in section 4 are always fixed and cannot adapt to data as PsyGA can. Perhaps the most important difference between PsyGA and the indicator regularizer, however, is that the indicator regularizer forces costs to lie in a small subspace spanned by finitely many basis functions, whereas PsyGA allows for any cost function. So there is no any more restriction in the space of the cost functions as much as it was before. So let me see if there are questions so far. No? Okay. So our choice of PsyGA is motivated by the following fact shown in the appendix, which is that if we apply this PsyGA on the occupancy measure matching, then there is a proof that they have that this is equivalent to having this formulation over here, where we are maximizing the we're taking the max of the logarithm of d in state and action, where d is a discriminative classifier that returns values in 0, 1, plus this other term that is over the policy of the expert, where they are maximizing the logarithm of 1 minus d. And you might say, okay, what does this mean? This is exactly what it's typically optimized in a GAN. So you should have seen these already. We can now understand better the details. So equation 15, which is the following over here, and which comes out of this is, let's see what it is. Treating the causal entropy H as a policy regularizer controlled by lambda, we obtain a new mutation learning algorithm, which is the following, which is nothing else than this thing over here plus this entropy term, which finds a policy was measure, occupancy measure minimizes the Jensen-Shannon divergence to the experts. So this is minimizing this divergence over here. Equation 15 draws a connection between imitation learning and generative adversarial networks, which train a generative model G by having it confuse a discriminative classifier D. The job of D is to distinguish between the distribution of data generated by G and the true data distribution, where when D cannot distinguish data generated by G from the true data, then G has successfully matched the true data. In our setting, the learner's occupancy measure, rho pi, is analogous to the data distribution generated by G, and the expert occupancy measure, rho pi e, sorry, is analogous to the true data distribution. Okay, so here they are trying to have the policy, learned policy, get this discriminator confused as much as possible, while the discriminator is looking at the expert data. So this is basically our generator, the policy, that we're learning will be our generator, which will try to make the discriminators confused as much as possible by by basically imitating the expert trajectories. Uh, okay, we now present a practical algorithm which we call generative adversarial imitation learning for solving equation 15 for model-free imitation in large environments. Explicitly, we wish to find a saddle point in pi and d of the expression of this expression, which is the formula that we have seen before, with the addition of the entropy. So, and again, this is what you have typically in a GAN, where D has to try to distinguish between the data that are generated by the generator and the true data. And G has to try instead to match as much as possible the data that are the true data in such a way to make the discriminator confused. Okay. To do so, we first introduce a function approximator for pi and d. We will fit a parameterized policy pi theta with weights theta and a discriminator network d in 0, 1 with weights w. Then we alternate between an Adam gradient step on w to increase equation 16 with respect to d and a TRPO step on theta to decrease equation 16 with respect to pi. So TRPO, you have seen that already mentioned last week when we were looking at PPO. So TRPO is trust region policy optimization algorithm, where we're basically doing similar things to what we have seen for PPO. We're trying during the optimization to not change too much the policy in the gradient steps. So the TRPO prevents the policy from changing too much due to noise in the policy gradient. The discriminator network can be interpreted as a local cost function, providing a learning signal to the policy, and specifically taking a policy step that decreases the expected cost with respect to the cost function equal to the logarithm of this d. And it will move towards expert-like regions of state action space as classified by the discriminator. Okay. So let's look again a bit more in detail at this formula, right? So so we're trying to have a setting where this d that represents basically the cost function, because the logarithm of d is the cost function, right? So if the logarithm of d is the cost function, we're trying to have a situation where we are maximizing we're trying to maximize the the policy in such a way that can match the cost function that is generated by the cost function over the data that is generated by the expert. So it's trying to learn here, the discriminator is trying to learn a cost function that is recognizing the expert data, and it's differentiating the expert data by the ones of the policy. And at the same time, we're trying to learn a policy that minimizes this cost function, so it matches the data of the expert as much as possible so that the discriminator can get confused. And it's exactly what we have seen at the beginning if you look at this. So if you look at the here, if you look at this, it's exactly what we have seen at the beginning, right? It's the goal of all of this was trying to get in a situation where the uh, expert cost function was minimal, and so we are trying to optimize over the cost function over here, right? Where this should be minimal for the expert data, and at the same time, the policy is trying to go as close as possible to the expert data because it's minimizing the cost function itself. So it's trying to go as close as possible to the expert data so that the cost function is minimal. So the cost function is minimal, but at the same time, we're trying to maximize that. So it's sort of fighting one the other to find this equilibrium point. Okay, so the final algorithm over here is the following. So we have a bunch of expert trajectories for in a bunch of iterations. We sample trajectories. We update the discriminator parameters uh, with this gradient over here. Then we take a policy step using TRPO rule with the cost function logarithm of d of SA, uh, and specifically take a KL constrained natural gradient step. So it's again using KL divergence to avoid that the policy changes too much when taking the gradient step. Um, okay, so before we move on to the section of the experiments, questions regarding this? Any questions? Okay, formula. Can you repeat formula 15, please? So, formula 15 is just adding the entropy regularizer to uh, to do the imitation learning algorithm. So this is just adding this, and it's just saying that um, this term over here is equivalent to this Jensen-Shannon divergence to the expert. Okay, so is this Jensen-Shannon divergence is a squared metric between uh, distributions, and it's defined in terms of KL divergence. So again, it's just saying that the distribution of data shouldn't be um, uh, different too much. Um, okay, so now this is defined in terms of equation 14 then. So we can look at the detail of this. Equation 14 is the optimal negative log loss uh, of the binary classification problem of distinguishing between state action pairs of pi and pi e. Okay, so here we're doing an optimization over D, which is our discriminator, our discriminative classifier, which is this classifier is trying to I mean, this is a log loss. You should have seen this already in the machine learning course. And it's casting this problem as a binary classification problem, and it's trying to learn to distinguish between the data of the expert and the data uh, of the imitator. Let's call it this way, or any other policy. Okay. Um, then it's adding in this equation 15, it's adding an additional thing where it's saying, okay, over this, we want to also minimize the this cost over the policy, which means we want to find the best policy for which this, if we treat it as a cost function, it's um, um, it's hard for the discriminator, for this classifier, to distinguish between uh, the data of the policy and the data of the experts. And if you look at this translates to the equation that we were looking at the beginning in a very close way, which is this one, right? Where we said we're trying to find the best policy as possible that minimizes the cost function, and at the same time we're trying to maximize the cost function in such a way that the cost of any other policy is high compared to the cost of the expert. And this is the same thing that is happening here, because if you look at equation 15, it's saying we want to minimize the policy over the policy, sorry, this objective, and this objective the only thing that we can do to minimize over the policy is minimize over this term over here, and we this means that we're treating this as a cost function, right? So now the other thing that we're doing is we're trying to maximize this cost function at the same time, such a way that it can discriminate between the policy that we're learning and the expert data. Now, this is not exactly matching the formulation that we had before, because this is using a log loss. So in a binary classification form, which means that if you are maximizing, I mean, you are maximizing the logarithm of d for one set of data and the logarithm of 1 minus d for the other set of data. So you want your um, discriminator to distinguish in the best way uh, these these two data. Now, if you don't recall how the log loss behaves, is I mean, we can look at this more in the detail. So um, so ideally, what we want is that for uh, pi e, the expert data, we um, have the discriminator returning us 0, and uh, for the policy data, with the ones that we're learning, to return 1. Why? Because if you look at this optimization over here, if this returns 0, then we have this logarithm of 1 over here, and this doesn't incur in any penalty, right? Um, or actually vice versa, the 0 and 1, but yeah, sure. The idea is the same. So you want these to find the discriminator to match the data over pi to be able to classify them in a certain way, and over pi e to classify them in the other way. And this is how the log loss is defining our optimization problem. And then in addition to this, we're doing this minimization here, where we're trying to find the best policy that optimizes this term, which means it's minimizing this term, which is then minimizing something which is the cost function. So if you replace logs of the SA with C, then this would be the cost function, right? Because which is why we have this additional definition over here where they say, okay, then C for us is the log of the SA. I don't know if this clarified or not. Can you answer if it is more clear or not? And I don't know if you have seen the log loss in the machine learning course. If not, we can look at that more in detail. Did you see the log loss? Can somebody tell me if you have seen the log loss in the machine learning course? Uh, is it possible to have one answer on this? Can somebody comment on the uh, either in the chat or in Slido to know, just to know if you know what the log loss is, and if I should spend more time on that. Okay, so let me show you one image. I think I will find it here. Here, okay. Uh, okay. Okay, so the discriminator, I mean, is operating on a log loss, which means that it's acting as a probability classifier over some data. Okay, and as I mentioned, it has to learn to distinguish mm, groups of data that might be belong to the different categories. One is the expert data in our case, and the other one is the other policy data. So here is one example. So the red is this is the telling us information regarding the actual true label. So if it's an actual 0 and it's an actual 1, so it's an actual expert data or it's an actual uh, non-expert data. And if the true label is 0, but the model predicts with zero point 0.9 confidence that the label is 1, then the log loss will be high, right? So the it's at 0 because it's red, and our model is telling us with 0.9 confidence that instead 1, then it will why it's telling us 0.9 confidence that is 1 because it's emitting 0.9. So either if it goes to emit 0, then it's telling us it's 0. Otherwise, it's telling us that it's a 1. So this is telling us 0.9, which means that it's thinking it's a 1. And in this case, the loss will be high. And the closer it gets to 1, the higher it is the loss. Similar thing for actual ones. So if this is uh, an actual 1 and the classifier is predicting 0.1, then in 0.1, if we look at this curve, then the classifier is receiving a high penalty, and this is in this penalty is increasing with the closer the estimated probability goes to 0. And this is how this is behaving in equation 15, and then as a consequence in equation 14. So um, that's it. So it's really just this. Okay, if you have more questions, you can ask them later. So let's look at the experiments. So we evaluated algorithm 1 against baselines on 9 physics-based control tasks, ranging from low-dimensional control tasks from the classic reinforcement learning in literature, the carpool, acrobot, and mountain car, to difficult high-dimensional tasks such as 3D humanoid locomotion, solved only recently by model-free reinforcement learning algorithms. Each task comes with a true cost function defined by the OpenAI gym. So how did they generate an expert? Just for experimental reasons, they first generate expert behavior for this task by running TRPO, the TRPO algorithm on this true cost function. So they use reinforcement learning to create an expert, and then they use this expert to generate some trajectories, and then they evaluate how well they can imitate that. To evaluate imitation performance with respect to sample complexity of expert data, we sample dataset of varying trajectory counts from expert policies. The trajectory constituting each dataset each consisted of about 50 state action pairs, and they compare against behavior cloning, feeder expectation matching, and game theoretical apprenticeship learning, which is another algorithm. We use all algorithms to train policies of the same neural network architectures for all tasks, 2 hidden layers of 100 units each, with 10 each non-linearities in between. The discriminator network for algorithm 1 also used the same architecture. All networks were always initialized randomly at the start of each trial. For each task, we gave FEM-GTAL and algorithm 1 exactly the same amount of environment interactions for training. So algorithm 1 depicts the result, and the tables in Appendix B, which we were not going to look at, provide exact performance numbers. And as you see, so they scaled the performance over the best performance that they got from any algorithm, which is basically always Gale. So as you see, these are the number of on the x-axis, you have the number of trajectories in the dataset, and on the y-axis, the performance. So if you look at this, the number of trajectories that are required by Gale in order to do imitation with the best performance that they get is very reduced. Basically, for carpool, acrobot, and mountain car, they can do that from the very beginning with one trajectory, similar for half theta, and uh, yeah, also, I mean, similar. Half theta requires four trajectories. Also, Hopper, Walker, and humanoid. These are the most complex ones. These are the simple ones, and uh, uh, just I mean, for this means that also the sample complexity that is required by this algorithm is very limited. So to conclude, they say our approach builds upon a vast line of work on inverse reinforcement learning, and hence, just like inverse reinforcement learning, our approach does not interact with the expert during training. Our method explores randomly to determine which actions bring a policy's occupancy measure closer to the experts, whereas method that do interact with the expert, like Dagger, which is another method we didn't look at, can simply ask the expert for such actions. So, we believe that the method that combines well-chosen environment models with expert interaction will win in terms of sample complexity of both expert and environment interaction. So this is the conclusion of this paper. And let's see if there are more questions regarding this. We are actually done for today. Questions, question time. I didn't get any answer yet. If somebody can answer me on the on whether you did see the log loss in machine learning course, I would be happy. Uh, but mm, thanks for the answer, girl. Okay, it seems like there are no questions, and thanks for answering me regarding the log loss thing. So I think we are done. We will see each other again uh, tomorrow, and which will be our last class. We will answer. We'll do the streaming just of the QA session, and then for the project presentation, we will not be streaming on YouTube, as well as for the presentation of the research work that uses reinforcement learning that I will shortly present. I mean, that's really